Good afternoon. Good morning. Here, the AICTE Prerana scheme for preparing AAC, SC and ST students for their higher education, uh, which was proceeded under the subject of circuit theory, under the topic is resonance. And myself, S. Selvi, belongs to the Department of Electrical Electronics Engineering of Erode Engineering College. Uh, Going to the present about the resonance topic. So today we just discuss about the topic of resonance. So first of all, we have to know what is meant by resonance. So these are all the topics which we're going to cover. That is Q magnification factor of resonance circuit, bandwidth of resonance circuit, and tuning, then analysis of parallel resonance circuit, damping of parallel resonance, choosing LNC of a resonance circuit. So in the resonance effect, the inductive, first of all, we have to know what is meant by resonance. A resonance means XL is equal to XC. If a circuit which satisfies the condition of XL is equal to XC, that is the inductive reactance is equal to the capacitive reactance, that can be seen as a resonance. So here inductive reactance increases as the frequency is also be increased, but the capacitive reactance will be decreased because it is inversely proportional to the frequency. So with higher frequencies. So based on that only here, commonly say the opposite characteristics for any LC combinations. Okay, for LC combination, there must be a frequency at which the XL will be equal to XC. Which one increases while the other will be decreases. If XL will be increases, the XC will be decreases here. So in this case, what is meant by resonance means the equal and opposite reactance is called as a resonance, right? And the AC circuit is then called as a resonance circuit. So at this resonance condition, the circuit will be called as a resonance circuit. And then frequency at which XL is equal to XC is called as a resonant frequency. So the frequency which occur in the circuit at the condition, or it satisfies the condition of XL is equal to XC, right? So this is a resonance effect. The most common application of the resonance is RF circuit, which is a tuning circuit, which can also seen as a tuning circuit. So from this figure, this is an LC circuit which having a resonant LC circuit is inbuilt, and it produces the maximum output of 1000 kilohertz. That is a maximum output which is produced from this resonant LC circuit. So here we just giving an n number of frequencies here from lower level to higher level of frequencies. When we feeding the lower level to higher level of frequencies, the resonant circuit will resonate by F4 is equal to 1 by 2 pi root of LC, and it will be produced maximum output at 1000 kilohertz. So based on this, the resonance will be occur in circuits. So if that resonance is occurred in a series circuit, then it will be called as a series resonance, and as then the resonance will be occur in a parallel circuit, it will be called as a parallel circuit. Commonly resonance will be occurred in common RLC circuits, right? So for this a series resonance, in the series resonance, first, we discuss about the series resonance. In that series resonance, a resonant frequency of the inductive reactance and the capacitive reactance or will be equal. Both will be equal. Then only the resonance frequency is occur. So in this circuit, in a series AC circuit, an inductive reactance leads by a 90-degree where compared with the zero reference angle, and which is capacitive reactance is lags by the 90-degree. So your inductive reactance is leads by 90-degree, whereas your capacitive reactance lags by 90-degree. Then only that particular circuit will act as a pure resistive. So here, these are all the reference with the resistance, right? So at that condition, your XL and XC both are in out of phase, that is 180-degree out of phase. the opposite reactants which can cancels each other completely because they are opposite, right? XL is equal to XC. XL is 90 degree, XC is minus 90 degree. So both will be is in out of phase. So it will be opposite reactant. So it will cancel each other. This is a series resonance circuit. In the series resonance circuit, here F4 will be as in a series resonant frequency, and L is an inductance, which capacitance C is in a capacitance. So resonant frequency F4 is equal to commonly is 1 divided by 2 pi root of LC. This is resonant frequency for series circuit, right? So here in this case, you just take a circuit with having a series connection of RLC, which is fed by AC input supply, right? And in this case, XL and XC is equal. Then the net reactance of the both the things will be 0 ohms. See here, your XL value is 1500 ohm, as well as your XC is also 1500 ohm. So both the reactance is equal. Then it will cancel each other. The only opposition of the current is the coil resistance, that is RS. Okay, which only limits the flow of current, but here it happens how low the series resistance in the circuit. So the resistance value is only 10 ohm. The giving input is 300 microvolt. So the current is the maximum current is allowed to pass in this circuit. So for that, we just giving the characteristics here. Let's discuss this circuit, right? So in this case, we having RLC, right? R value is 4 ohm, XC is 31, XL is 31. So both the things are same, that is your XC is equal to XL, so the two things will be same. So from this we have to finding the current value determined panel. See here, where IR is equal to 20 divided by 4. So in this case, the total current flowing in the circuit is 5 amps here, and the voltage across the individual storage elements. So here we are using the storage elements. So commonly we just determining the resonance uh, in a circuit which presents a storage element. If there is a no storage element, there is a no frequency will be occurred there. So that's why always we just finding the resonance only in the RLC circuit. Either it is in series or it is in a parallel circuit. So in this case, that VL will be taken here as I into XL. This is a common formula from your Ohm's law. V is equal to IR. Based on that, here the voltage across the inductance VL is equal to the current flowing through this circuit into the reactance present in your inductor, that is XL, which is equal to 155 volt. The same thing we just determining where VC is equal to I into XC, that is equal to 155 volt, right? So in this case here, your VL, VC, both will be same, but the phasor will be different because the inductance which leads your voltage, where capacitance lags voltage, right? So the phasor will be different, so it becomes 0. That's why your VXL plus VXC is equal to 0, right? See that thing in this case also. So we're just seeing the resonant rise in VL and VC. Okay, so the resonant that is the resonant frequency is rising from VL to VC. In this case, see here the charge, that is a Q is equal to 7.8, and here in this circuit here Q is equal to 32, right? So in this case, where VL is equal to I into XL, this is commonly we just determine 155 volt, and VC equal to I into XC equal to 155 volt. So based on this, 7.8 into 20 volt, that is nothing as 150, that is Q. This is a charge, right? Q 7.8 into 20 volt, which is also be equal to 125. Right, this is the common voltage. So this is a common voltage which is spreading to here, right? At same, then VL, I into XL. So here I is 5, your XL is 4, 640. The same similarly like this. This is also 640. The voltage across the capacitance is also 640. So both the VL, VC is same here. So in this case, the Vx is also B, Q is 32 and voltage is 20. So when you multiply in V into I, that's based on that Q 32 into 20, which gives us a 640 volt, right? So based on that, we have to determine the frequency response. Frequency response as nothing as a resonant frequency. We already determined the resonant frequency, that FR is equal to 1 divided by 2 pi root of LC, which is equal to 1 divided by 2 pi root of 1 into 10 power minus 3 into 1 into 10 power minus 6. So when you're calculating this, we can get the frequency as 5.03 kilohertz. So from this, we just plotting the graph between the current and frequency. The current value is 5 ampere. In the 5 ampere, the frequency only we get as a peak, that is a 5.03 kilohertz, right? So we're just plotting the graph. So series RLC circuit, we just discuss some of the properties followed in series RLC circuit, RLC. So first, let us define what we already know about some of the properties in series RLC circuit is inductive reactance. So we know where inductive reactance is XL. XL is equal to 2 pi F into L, which is nothing can be called as an omega L. So this is a very important formula which will be used in all aspects, right? So in capacitive reactance, where Xc is equal to 1 divided by 2 pi Fc, that is 1 by omega C. If if in case two parameters in RLC circuit, we are having both XL, Xc, both are present. So in that case, when the circuit will be act as inductive and when the circuit will be act as a capacitive, means based on the two categories, that is whether your XL is greater than Xc, then the circuit will behave as an inductive circuit. If Xc is greater than XL, then the particular circuit will behave as a capacitive circuit. The total circuit reactance is Xt is equal to XL minus Xc, or whereas an Xc minus XL. And the total impedance of the particular circuit is where Z equal to root of R square plus total reactance, a total reactance which is nothing as XL minus Xc the whole square. Okay. From the based on these equations, the inductive reactance, either the frequency or the inductance will be increased. So based on this, see here, based on the inductive reactance, it is directly proportional to your frequency. If the inductive reactance will be increases, then the frequency will be increases. Then depends upon the capacitive reactance. If the capacitive reactance will be increases, your frequency will be decreases. If your frequency will be increases higher, the capacitive reactance will be decreases here. So that is a thing which we will explain here. If either the frequency or the inductance is increased, the overall inductive reactance value of the particular inductor would also be increases. As the frequency which approaches infinity, the inductors, reactors would also be increases towards the infinity with the particular circuit element which was acting like an open circuit, right? And if the frequency which reaches to the zero value, if it will be reaches to the zero value, or it may be as in a DC, the inductor reactance would be decreases to zero by causing an opposite effect like a short circuit effect. So before it will be act as an open circuit. In this case, if your frequency which reduces, then at the time it will be act as a short circuit. So this means it is directly proportional. That only be explained here, that XL is directly proportional to your frequency, right? So that is your inductive reactance is directly proportional to your frequency, and it is very small at low frequencies and high at higher frequencies. and it will be demonstrated by the curve by using inductive reactance against the frequency. See here the reactance with comparing with your frequency. So when you're comparing these two things, it produces the linear curve, right? So that is only explained as straight line of linear curve. So in the inductive reactance, the value of an inductor increases linearly as the the frequency will also be increases. Both your reactance increases as well as the frequency will be increases. So it will produces a linear curve. Therefore, the inductive reactance is produces in positive and it is directly proportional to the frequency. Inductive reactance against the frequency, that will be as the same for the capacitive reactance formula where reversed. So because your Xc is equal to 1 by F. If either the frequency or the capacitance is increased, the overall capacitive reactance would decrease because it is inversely proportional here. So for that, the frequency which approaches to infinity, the capacitor reactance would be reduces to practically zero, because that causing the circuit element as a perfect conductor of 0 ohm. There is a no resistance is there. So it allows the current to flow, right? So these are all the very important minute questions which we are also asked in 1 marks. So the capacitive reactance which was rapidly increased up to infinity, that causing it and that act like a very large resistance, which becoming more like an open circuit condition. So in this case, the capacitive reactance is inversely proportional to your frequency. So the graph of the capacitive reactance against the frequency, which is an hyperbolic curve. So based on that, the reactance value of a capacitor has a very high value at low frequency, but quickly decreases to the frequency which across it increases. Therefore, the capacitive reactance is negative. Capacitive reactance will be negative and is inversely proportional to the frequency. So let capacitive reactance against your frequency, right? So let us the resistance which depends on the frequency. Okay, it depends upon the frequency of the particular supply. Then we just applying the higher frequency. We just increasing the frequency. Then the XL is also be increased. And at a low frequency, your XC will be high. If frequency increases, XL will be high. If the frequency is low, then XC is high, right? There must be a frequency point where the value of XL is same as the value of XC. But the XL XC is same, right? XL XC is same here. We just varying only frequency. High frequency, high inductive reactance. Low frequency, high capacitive reactance. But the XL XC is same. Clear? If we now place the curve for inductive reactance on top of the curve for capacitive reactance, right? So where both curves are on the same axis, the point of intersection will give as a series resonance frequency. That's where F or it may be represented as omega r. So see here. So in this only we just seen before. So in this case, see, if your reactance will be increased, the frequency will be increased linearly. But if you're increasing the frequency, your reactance will become lower. It will be decreased. Okay. So the meeting at the point is in this point only XL XC will be equal. So in this case, your frequency will be increases, then XL will be increases. Here your frequency will be reduces, but your XC will be increases, right? So at that point only meet as an XL equal to X. So this point is as an resonant. This is a resonant point. So before the resonant, the circuit which behave as a capacitive. After the resonant, the circuit will behave as an inductive. So at that condition, in before the resonant, the XC will be greater than XL. At the time, the circuit which behave as a capacitive circuit. After the resonant period, your XL is greater than XC. At that time, the circuit which behave as a inductive circuit. Right? So this is a electrical resonance which occurs in an AC circuit when the two reactants which are in opposite and equal and cancel each other. Then out is XL is equal to XC, and the point on the graph at which this happens is where the two reactance curves also cross each other. In the series resonant point, the resonant frequency F4 can be calculated by using some formulas, that is where XL and XC is equal. We can commonly mention as 2 pi FL is equal to 1 by 2 pi FC. And also based on that, where F square is equal to, based on this, you just cross multiplying F square equal to 1 by 2 F 2 pi C into 2 pi L. So 2 pi, which is 1 by 4 pi square LC. This is F square, taking square root. F is equal to square root of 1 divided by 4 pi square LC. So F square, so it is taken from the out of square root 1 divided by 2 pi root of LC. This is the resonance frequency. So this can be also called that omega r is equal to 1 by root of LC. That is omega equal to 2 pi f. So 2 pi f will be cross multiplied here. When you cross multiply 2 pi f r, that will be mentioned as a omega r. So we can see a resonance that the two reactants which cancel each other out, thereby making a series LC combination, which act as a short circuit with the one-way opposition to current flow in a series resonance circuit, which being the resistance R. In complex form, the resonant frequency is a frequency at which the total impedance of a series RLC circuit which becomes purely real and there is no imaginary, because in that circuit the real part R only be present. There is a no imaginary part, right? That imaginary part is exists. Imaginary impedances exist. No imaginary impedance present. So this is because at resonance they are cancel each other. So the total impedance of the series circuit becomes just the value of the resistance, and therefore where Z equal to R. Z equal to R. The total Z equal to R value. Then at resonance, the impedance of the series circuit is minimum value and it is equal to resistance. Very minimum resistance will be equal to a impedance that only mentioned as an Z equal to R. So in this circuit, the impedance at the resonance is a dynamic, that is called as a dynamic impedance, where Z naught is equal to R, which is called as a dynamic impedance of the circuit, and depending upon the frequency Xc, which typically at higher frequencies, or XL will dominate either side of the resonance, right? So you just note that in capacitive reactance dominating the circuit, the impedance curve which has a parabolic curve. In this parabolic curve, the inductive reactance dominates the circuit. The curve is non-symmetrical due to the linear response of XL. So already I told that Z equal to R, it's having a very minimum resistance value. There is a no imaginary part, only real parts are present. So where Z equal to R here. So at the resonance, before the resonance, that circuit will behave as a capacitor. After the resonance, the circuit will behave as an inductor. Right? And another property, this is the one property, that is impedance. And another property is admittance. What is admittance? Admittance is the inverse of your impedance is called as an admittance, which is nothing as y is equal to 1 by z. So if z is very minimum, then what happens in admittance? It is of inversely proportional. So it just maximum. If your impedance is minimum, then your admittance will be maximum. Right? So that is only he explained. And one of the characteristics of the series resonance circuit is that admittance, which is very high. And in this, it can be very bad thing because of very low value of resistance is present at resonance condition. So that will be resulting the current flowing through the circuit, which cause very dangerous in the particular circuit is very high. So in the previous thing, a series RLC circuit, that voltage across a series combination is nothing as VR, VL, VC. If the resonance that occur, the two reactants are equal and cancelling each other, then the two voltages VL, VC must be as in also opposite and equal in value, thereby cancelling each other output, because with few components, the phasor voltages are taken as plus 90 degree and minus 90 degree respectively. So that the series resonance circuit as VL is equal to minus VC. Okay, this is one important thing you have to note, that is VL is equal to minus VC. So in this case, the resulting reactive voltages are zero and the supply voltage is dropped across the resistor. So therefore, VR is equal to V supply. That is the voltage across the resistance equal to supply voltage. And it is for this reason the series resonance circuits are known as voltage resonance circuits, as opposed to parallel resonance circuit, which are current resonance circuit. That is a opposed to called parallel resonance circuit, which is normally say as a current resonance circuit. Okay. So the series RLC circuit at resonance. See here, the either side of the resonance will having the voltage drop, voltage across VL and voltage across the capacitance. So where VL minus VC. So if the resonance of the voltage drop is equal to zero means, then it will be commonly short circuited. Your LC is short circuited. So across this, there is a no voltage, that is a zero voltage. So in this case, if the resonance will be presence means at the resonance point the current is maximum, because there is a no storage elements. L and C will cancel each other. It will behave as a short circuit, and the resistance is very minimum. At that point, the current, the flowing of current is very higher in that point. So the peak current is produced. That is only here mentioned as an I max. So, and we're just comparing the with the phase angle. In this phase angle, here the first case capacitive. In the capacitive, your XC is greater than of XL. At the time, your VC, the voltage across the capacitor, and the voltage across the inductor, that is VL, VC. VC is greater than your VL. At that time, the current and voltage. So in this case, see here, the current will be starts before theta value, and after the theta only the voltage will be induced. So the voltage lags behind your current by 90 degree, right? So it will be lagging means that will be is it negative. So minus, it having a negative. Then both the voltage and current will be same. Both is in end phase at resonance. At resonance means commonly say at resonance your XL is equal to XC, as well as your power factor is unity, and your voltage across the inductor and capacitor both should be is in unity. So based on that, at that condition where I in phase with Vs, so I is in phase means both voltage and current should be is in phase. So that is in phase at this point, right? So then above some frequency, when we increasing the frequency level above the resonant frequency, at that condition, the inductive reactance is greater than your capacitive reactance. So as well as the voltage across the inductor is greater than the voltage across the capacitor. Right? So in this case, the current which lags behind your voltage by 90 degree. So the current lags behind the current lags behind the voltage by 90 degree means it produces the positive 90 degree. At the condition, the voltage is leads your current by 90 degree. That statement is also right. So based on that statement, your phase angle is produced in positive sign. So and the bandwidth of the series resonance circuit, the bandwidth in between this bandwidth, this is a very very important topic. The bandwidth means commonly in between the two frequency level, uh, in between the lower level, upper level frequencies. The resonant frequency will be occur. There is a bandwidth, common bandwidth. So see here, in this case, the current is maximum. So in between this, we having the lower frequency and higher frequency. So in this in between these things will be called as a bandwidth, right? So when uh, we have to produce a different level of current and frequency means we just changing the resistance value. If you change the resistance value, a high when resistance is very small, the current is high. If the R is medium, based upon that, the current is also mediumly it will be passing. If the R is high, then your current is very low and it is very minimum. So that is a relationship which was given between the resonance bandwidth, selectivity, and quality factor. Quality factor, which is nothing else than a Q factor. A Q factor is now called as normally called as the magnification. In the magnification, that will be called either Q magnification or Q factor or figure of merit. So in any other words, they may be asked. So the relationship between these things, resonance and all the things, bandwidth, selectivity, quality factor, or so first resonant frequency. The resonant frequency which occurs at condition XL is equal to XC. So at the time omega RL is minus 1 divided by omega RC equal to 0. Omega R square equal to 1 divided by LC, and then omega R equal to 1 divided by root of LC. Right? So based on the current, that impedance is minimum, but your current is maximum. If impedance is nothing as a resistance, both the things, both resistance and impedance is minimum, then the current is maximum. So it will be expressed in terms I max equal to V max divided by Z, which is equal to V max divided by root of R square plus, that is V by Z. Z formula is R root of R square plus XL minus XC the whole square. So lower cutoff frequency and higher cutoff frequency. In lower cutoff frequency, the lower value, that is at half power, the power Pm by 2, which is nothing else, I is equal to Im by root 2. Right? So this is an a half power value 0.707 Im. Then impedance is equal to root 2 Rx and equal to R, which is nothing else than a capacitive circuit. So whereas an omega L equal to R by 2L, R by 2L plus the root of, because this is a half of the power, so everything is in a half case. So R divided by 2L, the whole square plus 1 by LC. And for upper cutoff frequency, in upper cutoff frequency, where is it equal to root, in upper cutoff frequency, is that equal to root 2r, where x equal to plus r. At that condition, it will behave as an inductive, where frequency omega h equal to r by 2l plus root of r by 2l the whole square plus 1 by lc. Right? So, and the bandwidth is between the range which is between fh to fl, right? So that will be expressed the resonant frequency f divided by q, or fh minus, sorry, fh minus fl. That is in terms of radians. Then quality factor, which is nothing as q factor. Q factor, Q is equal to omega r L divided by R, then XL divided by R, and for capacitor 1 divided by omega R into CR, that is nothing XC by R. So when you equating this and calculating, you can get 1 divided by R root of LC. You have to remember these things, then only we can solve the problem. Okay, so up to this, we just recollect and revise the terminologies which we are used in the series resonance topic. This series resonance topic under that. So next we just discuss about the problem. So see the problem. And read the problem which we are shown. A series resonance. See the problem, that is a series resonance network which consisting of a resistor of 30 ohm and a capacitor of 2 microfarad and an inductor of 20 millihenry is connected across a sinusoidal supply voltage. Right? Sinusoidal supply voltage, which has the constant output of 9 volt at all frequencies, and calculate the resonant frequency, the current at resonance condition. That is, we have to calculate the resonant frequency and the current at resonance condition. Then the voltage across the inductor and the capacitor at resonance. Then the quality factor and the bandwidth of the circuit. So we have to calculate all those things. Also check the corresponding current waveform for all frequencies. Okay. So the problem is given under common thing. That is, this is RLC circuit. In this RLC circuit, we having a parameter of 30 ohm and capacitor of 2 microfarad and inductor of 20 millihenry, right? And in that, we just giving input supplied as a AC input supplied, and has a constant output is 9 volt at all frequencies. At all frequencies, calculate the resonant frequency, current at resonance, voltage across the inductor and capacitor at resonance, the quality factor and the bandwidth of the circuit. Also, also check that the current waveform in all frequencies. So this is a circuit, so which we giving the input voltage as 9 volt. For that, we just working a and a RLC circuit. So from that, first we have to calculate the resonant frequency. For resonant frequency, we know the formula as F4 is equal to 1 divided by 2 pi root of LC. Root of LC. So in this case, 1 divided by 2 pi root of L value is 0.02 and C value is 2 into 10 power minus 6. When you're calculating this, you can get 796 hertz, right? So then circuit current, that is circuit current, this condition, if sometimes the current is peak or it will be decreased, depends upon the resistance value. The current flowing in the circuit will be varies, so that the circuit current at resonance, the circuit current at resonance, which is I is equal to V by R. This is a common formula which we are used commonly. I is equal to V by R, that is your V is 9 and R is 90, sorry, R is 30. So when you calculating this, you can get 0.3 ampere, right? Or it may be written as 300 milliampere, right? So then inductive reactance and inductive reactance at resonance. Inductive reactance at resonance is XL. XL equal to 2 pi FL, that is 2 pi F value is 796, that is we have to use here resonant frequency, not common frequency. So in this case, we have to use all in this all frequencies we have to use a resonant frequency. So if they give a question at resonance means you have to use at resonance questions only. Okay. So that is XL equal to 2 pi FL, which is nothing 2 pi 7.96 into 0.02, that gives a 100 ohm. So then the voltage across the inductor and the capacitor. Voltage across the inductor and capacitor. So, or you calculate that where VL is equal to, because in this case XL equal to XC, same VL is equal to VC. So where VL equal to I into XL, your I value is already determined or under the value of Z, that is nothing R, right? So VL is equal to I into XL. Your I XL value is I is 300, XL is 100. So in this case, you have to determine the XL value. XL value can be determined by using the formula where XL equal to 2 pi FL. So From that, you can calculate the XL value. Your XL value is 100. So the VL, the voltage across the inductance is 30 volt. So in this case, the supply voltage may be only 9 volt, but the resonance will be varied one. So the reactive voltage across the capacitor VC and the inductor VL are 30 volts in peak. So the next thing is a quality factor. In this quality factor, Q, where Q equal to XL by R. So Q factor which having the formula as XL divided by R. As we can also use another formula which we are produced in series circuit. That formula can also be used. So in this case where Q is equal to XL by R, XL value is 100, which was previously determined where XL is equal to 100. So 100 by 30, that is your quality factor. Q factor is 3.33, right? And the bandwidth is BW is equal to F1 divided by Q. Resonance frequency is 796 divided by 3.33. So it produces the value of 238 hertz, right? And the last thing they just given in a question is have to check the current waveform for all frequencies. That's why here depends upon that the upper and lower 3 dB, that is a 3 decibel frequency points F, H, and FL. FH is in a high frequency, FL is a lower frequency. So we're just using the formula FL is equal to F1 minus half that BW, which is equal to 796 minus 1 by 2. BW is nothing else than a bandwidth, that is 238. When you're calculating this, the lower frequency level is 677 Hz, and higher frequency, the only changes is sign change, that is here. Lower frequency level minus, higher frequency level is plus. So when you're calculating this, you can get 915. So this is only the variation between uh, two levels of frequencies. So this is a current waveform. Your current value is maximum, that is 300 milliampere, and at that thing, the resonant lower frequency is 677, higher frequency is 950, and the medium frequency is 796. That is only the resonance will be occurred. Resonant frequency. Okay. Right. So based on this only, the individual current waveform for all frequencies will be measured. So the next problem is a series circuit which consists of a resistance of 4 ohm and an inductance of 500 millihenry and a variable capacitance which was connected across the 100 volt and 50 watt supply. Calculate the capacitance value that required to produce a resonance condition and the voltage generated across both the inductor and capacitor at the point of resonance. So the same problem which we was previously solved like that. The same problem here we have to calculate the same thing, that is a capacitance value T, right? We have to find the value of C and at resonance condition FR, we have to calculate the value of C and the voltage generated across both the inductor and the capacitor, that is voltage across L and the voltage across C. This is also be calculated at resonance point, right? So this may be calculated. This maybe try this problem. So after this, Up to this we just discussed. So in next class we can discuss about the parallel resonance. So in series resonance, you just work out the problems, solve some of the problems, right? Okay. So these are all the some parameters and properties of series resonance. Okay. So this questions uh, will be asked in the gate questions, that is in between reasoning questions, and if the statement is true like that, that is if reactance will be increased, then what about the frequency? If inductive reactance will be low, then what about your frequency? Capacitive reactance is higher, then what about your frequency? And what about the bandwidth? Like that, reasoning type of questions is also be asked, and the statement will be right or wrong. Like that type of questions also be asked, and based on that circuit, they may be asked some simple problems like to calculate the capacitance value at resonant condition, like, and quality factor, Q factor can also be asked to calculate, and bandwidth. So these different cases of questions which may be asked in the gate questions. So in next session, let's we discuss about the parallel resonance. After that, we can solve some problems in resonance. So thank you.